Hello guys, nice to see you.
Good afternoon.
Hi, good afternoon. Hello. So, how are you doing after weekend?
Not bad. What
Yes.
about you?
Yeah, also good. By Friday we'll be tired already, but on Monday have to feel good. So whole week still need to work. Yeah, hello everyone. So last time we discussed, finished our discussion of acoustic, like sound waves, and that was actually the uh, end of our first part of the course, end of mechanics. So today we start with a new part with thermodynamics and molecular physics. And today we will try to give some general introduction of what is thermodynamics, what it deals with, also what is temperature, how we can measure temperature, what are like some important moments to know about measuring temperature, and also we'll consider some quantitative moments related to expansion, linear and volumetric expansion of solids and liquid. So that's our plan for today. I think we can switch to our slides. And let's start from introducing thermodynamics, some general introduction. So thermodynamics studies how temperature and aggregate state of material, like it could be solid, liquid, or gaseous state, are changing due to the transfer of energy, in most cases in the form of heat. So thermodynamics is obviously determined by atomic nature of matter, but what is convenient actually for operating with thermodynamic principles, that it deals with macroscopical parameters such as pressure and temperature. So it means that those macroscopic parameters which can be easily and reliably with high accuracy measured. So we mentioned about temperature, and that definitely one of the key parameter for in the field of thermodynamics. And in general is defined as quantitative measure of internal energy and of some body or system. So how do we measure temperature? So we can touch an object, like for first approximation, and tell, okay, it's hot or cold, according to our subjective feelings. For someone could be hot, for someone warm, but that is quite difficult to quantify, and that's why we need something more reliable. So what kind of physical effect can be considered as a good platform for measuring temperature? So we know that objects thermally expand when temperature increases. So for instance, if we consider some rod of some material, doesn't matter which material, with some length L at T1, for instance. Then we increase temperature, so we go from T1 to T2, and T2 is higher than T1. That will cause some thermal expansion of this rod. So that will be delta L. And that delta L will be proportional to delta T, which is equal to T2 minus T1. So looks quite easy and straightforward. So we have some, for instance, metal rod. We measure its length at some 2 reference temperatures. And when we deal with, let's say at the beginning, we deal with degrees of Celsius. So we have 2 reference temperatures. One is 0 degrees Celsius when we have icy water, and boiling water provides us another reference temperature, 100 degrees Celsius. So that is obviously true at the sea level when pressure is equal to 1 atmosphere. So we have 2 reference points. We can measure length of this rod at 2 different reference points, divide this change of length by 100 steps between 0 and 100 degrees Celsius, and have corresponding lengths for any temperature in this range from 0 to 100. So pretty much done. However, as you noticed, we don't have wide application of such thermometers in everyday life. And any ideas what is the reason for that? Why we don't go for such thermometers?
They will be inconvenient, probably.
Yes, and what is the main problem with this type of thermometer? So we technically can measure. That will be, but you are right, it will be inconvenient. And main inconvenience will originate from this very weak dependence of delta L on delta T. So for small change of temperature from, let's say, consider from 0 to 100 degrees Celsius, change of length of this metal or any other material rod will be very, very small. So then it means that the accuracy of the measuring this small change of length will be not sufficient, or it will require really advanced methods and techniques to measure such small change in the length. So that is really impractical. So there should be some solution to this. And this is one of the problems which can be solved in the scope of material science, because we can use different material for the same purpose, but having some benefits of unique properties of different material in order to overcome those challenges and inconveniences which originated from properties of the previous first material. So in this case, its transition from solid state to liquid state makes a big difference. Why? Liquids also quite expand thermally quite little as solids. However, because of the properties of liquid, we can engineer liquid thermometer as some tube with reservoir filled with this working liquid, let's call it, or active material in the thermometer. And the fact that our tube has very small cross-section area, means very small diameter, even tiny change in the volume of this liquid will be quite visible, because this tiny change in volume will require quite significant displacement of the edge of this liquid upwards, and that we can see. So we cannot do such a trick with solid material, but liquid can fill such reservoir, which is usually made of glass, and then it works quite well. So liquid is a good solution. So that's why, as you know, liquid thermometers, they are quite common and widely used. Nowadays, it's more replaced by some thermoelectric thermometers. However, for certain purposes, liquid thermometers are very reliable and accurate instruments. So let us talk about this liquid. Can we put here any liquid, or this liquid should possess some properties? And which properties are important for ideal choice of liquid in liquid thermometer? Any suggestions? So can we use, for instance, water in such a thermometer?
Well, not really. I think hydrargyrum would be better.
Okay, so water is not the best choice, because we have this reference temperature 0 degrees Celsius when water freezes, and we want liquid to remain liquid in all temperature range we work. So that is important moment. So it should not freeze at temperatures which are within the range of those temperatures which we want to measure. So that is some obvious property of this liquid, which should be fulfilled. So you mentioned about hydrargyrum, which is mercury. That's absolutely right. And most accurate liquid thermometers, they indeed use mercury as working liquid. So the question is, what makes mercury so good for application in liquid thermometers? Besides the fact that it remains liquid until minus 40 degrees. Its specific gravity, that is interesting approach. I'm not sure what is specific gravity of mercury, but probably you mean that it's a very dense material. So that is a property of mercury. Its density is very high. And that's probably one of the main reasons why mercury is used to measure atmospheric pressure, because then we have to use much shorter pillar of mercury in comparison to water, for instance, to compensate atmospheric pressure. So that is the feature which is used in pressure measurements. However, it has nothing to do with the requirements for temperature measurements. There are other features. So another question which could help in this consideration: what is mercury? There are element, yeah, it is, but in terms of material, so is it some dielectric, semiconductor, or metal? Yeah, so it is a metal. And if you consider such a property as thermal conductivity, you will realize that thermal conductivity of metals is much higher than thermal conductivity of some other materials, for instance, some insulators. We usually put some insulating materials on our walls in order to prevent heat dissipation from our buildings. And we don't make our walls from metal. We use other materials, because if we make it from metal, all heat will immediately be transferred from inside to outside. And that is because of high thermal conductivity of metal. And that is the feature which is very important in thermometers, liquid thermometers. So how measurement of temperature is carried out? So let's say we have some surface of water of which we want to measure the temperature. We immerse this reservoir with mercury in this water, and we want the temperature of mercury will be the same all over the volume of this mercury as soon as possible in order to get accurate measurement. If we don't reach this equilibrium, so that we get the same temperature of mercury in whole volume of the thermometer, a part of mercury which will be on the outer sides of this volume will be at higher temperatures than internal volume of mercury, and in that case, will result in wrong readings of this thermometer. So we want this whole volume to be at the same temperature, which is in thermal equilibrium with the environment where we measure the temperature. So that is temperature of this liquid, TL. So because of very high thermal conductivity of mercury, this equilibrium is reached quite fast, and we have the same temperature everywhere in the volume of mercury inside liquid thermometer. That gives us accurate results in measuring temperature. So that is very important parameter. And nothing can compete with mercury since it's actually a liquid metal. So we use kind of, that's another thing of material science approach. We use mercury's thermal conductivity as a metal, but at the same time, we also use its unique feature of staying in liquid phase at quite wide temperature range up to -40 degrees Celsius, which makes it really a good candidate for measuring temperature in liquid thermometers. Moreover, there is another feature which makes mercury thermometers, liquid thermometers, more accurate than others. So let's say we don't care how much time it will take to get into equilibrium, then we can use, for instance, some alcohol. So some liquid alcohol, it has even some advantages because it doesn't freeze at -40 degrees, so you can measure even lower temperatures. And it will take a bit longer to get to equilibrium with environment where we measure temperature. But let's say we can wait for longer. We don't care about this feature. However, mercury will still be better in terms of accuracy of the measurement. The thing is that alcohol or water also quite efficiently water the surface of glass. Means that in this tube, it will form at the edges where water or alcohol touches this glass tube, it will form some menisc. So water will kind of, because of surface tension at the interface of interaction, the water surface with glass surface, there will be some menisc. So that's why when and how we measure temperature, we have some marks which correspond to different temperature, 40, 60, 80 degrees Celsius, for instance. So when we look at such pipe with alcohol inside, for instance, we see this level which corresponds to the position of this alcohol, but it interferes with these two meniscs. And that's why there is some uncertainty in the accurate position of the interface between filled area with alcohol and empty area. So that will result in some error in measuring temperature. Yeah, you have a question? Oh, okay, so it was just some noise. So the unique feature of another useful feature of mercury, that it doesn't water glass surface. Means if we have this glass tube, then mercury forms this menisc in opposite direction, downwards instead of upwards. And that's why we can clearly see where the edge of mercury is located. So then it's much easier to accurately measure temperature, specifically in some special thermometers, not those which we measure usually our body temperature, but those kind of some engineering thermometers which provide very high accuracy. There we have very fine marks closely located. And with mercury, active material in liquid thermometer, it's much easier to measure temperature. Before we proceed further, just one also comment about this measuring temperature with liquid thermometer, just to create this feeling that it's not so trivial to measure temperature with liquid thermometer. So how does it work? We have this reservoir. We assume that all, for instance, mercury is located in this reservoir. Then we put it inside water, for instance, water, where we want to measure temperature, and believe that all this mercury will reach thermal equilibrium with the environment, with the liquid, and will be at the same temperature as the environment. So eventually we will get this temperature. So that is largely true. However, not absolutely true. The thing is that when we increase temperature, then there is a small part of mercury which stands in this tube at level higher than our liquid. Means that small part of mercury will not be at the same temperature as liquid where we want to measure temperature. And that will result in some error in measuring temperature accurately. So that's why there is special information for, like in passports for thermometers, which provide appropriate coefficients and equations to take into account this error of the external pillar of the mercury, which is beyond the environment, like locates outside the environment in which we measure temperature. And that also depends on the difference in let's say, air temperature and liquid temperature. So the higher difference, the longer this, the higher this pillar of mercury outside the measuring environment, the larger will be this error. So that's just some comment that even measuring temperature with liquid thermometer requires quite a serious approach in order to get the highest accuracy. Oh, yeah, you are right. We can put located deeper. However, that is not common practice because you have some device, you fix the position of thermometer, it stays fixed, and you don't usually change the position of thermometer, since that could also change the properties of your device. So in order to have reproducible conditions, you keep everything the same in order to reproduce conditions of experiment. So you don't want to move any parts. The first thing. Second thing, that it's not just like this construction of thermometer. That's kind of simplified example, because we have something like reservoir with mercury. Then this reservoir with mercury goes into a very thin pipe. And in order to protect, because it's very brittle, it's very thin glass pipe, in order to protect it, it stays in some glass tube. So you even, there is only one place where we have a thin glass layer between mercury and measuring environment. Here we have some vacuum or air, and that's why even if we want to put them into contact, there will not be intimate contact, because even if we have here mercury and then we immerse it in liquid up to this level, this part still will not be in direct contact with the environment where we measure temperature, as opposite to this volume, because it will be isolated with this gap. So it's not so easy to do. And that's why there are special approaches and techniques which, and like coefficients and equations designed by manufacturer of the thermometers when they are going through calibration prior to selling, being sold, which allow to take this into account. Okay, so the thing is, the problem with liquid thermometers is that not in all temperature ranges where active material remains liquid, expansion happens linearly. So we believe that, let's say, thermal expansion of some linear expansion of some material is equal to alpha times initial length, for instance, times delta T. Or for volume, we can write delta V, change in volume, is beta, volumetric thermal expansion coefficient, times V initial times delta T. So that means that we consider linear dependence of expansion versus change in temperature. However, so that is true for some ranges of temperatures, but not for all ranges of temperatures. And different materials provide different ranges of temperatures where they exhibit this linear dependence. And we, for accurate measurements, obviously we want to have linear dependence, because we want to have at any point of this tube equal steps for 1 degree Celsius to have reproducible and reliable measurement. So in order to go beyond this problem, we can use so-called constant volume gas thermometer. So in this case, we will have some tube with a reservoir, and that is filled with gas. Here we have gas. We can immerse it also in some liquid in order to measure its changing temperature. And then we compensate this pressure to keep this gas in this volume with some pillar of mercury. So it's with a height h. What is important for this system? That we keep the volume constant. So we change temperature, but volume, so temperature is not constant. Volume remains constant. And in order to keep volume constant, for instance, if we increase temperature, we gas would like to expand. So in order to keep this volume constant, we need to increase pressure. So pressure is not constant. And that means we need to increase the height of this mercury pillar, which is not constant also. So if we increase height of the mercury pillar, we can compensate this thermal expansion of gas and keep it at the same constant. So then, again, we can address reference points, let's say 0 degrees Celsius and 100 degrees Celsius, measure pressure inside this gas versus temperature, and we will get some dependence, linear dependence in this case, in all very wide temperature range. And that will be a very good calibration thermometer. So how do we measure pressure? We consider pressure which is equal to P naught, pressure at, let's say, 0 degrees Celsius at some reference temperature, plus the change in this height of the mercury pillar. So it will be raw density of this liquid, which keeps the gas inside, times G times delta H. So that will give us the pressure inside. And if we have a plot, here will be temperature, let's say in degrees Celsius, here will be pressure. For two reference points, we will have, let's say, for 0 and 100 degrees Celsius, and then we will have linear dependence of pressure over temperature. So at every given pressure, we will know that it corresponds to certain temperature. What is interesting with this system, that if, for instance, we use different gases, we will get different slopes. It all will be linear dependencies, but slopes will be different. And if we extrapolate these linear dependencies towards negative temperatures, they will intercept at the same large negative temperature, which will be minus 273.15 degrees Celsius. And that is actually the absolute zero in absolute temperature. So in we can write that temperature in Celsius is equal to absolute temperature minus 273.15. And obviously absolute temperature is going from 0 Kelvin. So that is absolute zero. So also we can write that 1 degrees of Celsius is equal to 1 Kelvin. So absolute temperature, we usually use it quite often in physics, more often than degrees of Celsius. Moreover, there are other systems of measuring temperature for some like everyday use. Most common after degrees of Celsius is Fahrenheit, like degrees of Fahrenheit, which is widely spread in Northern America. So with this, we already clarified what is temperature and how we can approach measuring temperature. Now let us consider some features of thermal expansion of solids and liquids. So first, let us find a relationship between such two parameters as linear thermal expansion coefficient and volumetric thermal expansion coefficient. We already wrote these equations, but let us write it again. So its change in length will be equal to alpha times initial length times change in temperature. And for volume, change in volume, we can write similar, but we have this, this is linear expansion coefficient, thermal expansion coefficient. This is volumetric thermal expansion coefficient. Here we will have initial volume times change in temperature. So in order to find the relationship between them, let us consider some box with sides L, W, and H. So length, width, and height. At initial temperature T initial, initial volume of such box will be L times W times H. Then if we increase temperature, so we have T initial plus delta T, we will result in increase also in volume. So that will be V initial plus delta V. So now let us write here what will be equal this increased volume. So V plus delta V will be equal. So we can express it in terms of linear expansion of the sides of this box. So beta is alpha stands for linear thermal expansion coefficient, and beta stands for volumetric thermal expansion coefficients. Here you see change in length and change in volume. So we want to find the relationship between alpha and beta. So how can we highlight, like quantify this new increased volume? We can write that this will be product of L plus delta L, then times W plus delta W times H plus delta H. So also we can express this change in the length, width, and height in terms of alpha. So that will be L plus alpha times L times delta T. Then here will be W plus alpha times W times delta T, and H plus alpha times H times delta T. So now if we open all these parentheses and take out of parentheses the product of alpha, omega, h, here we will get 1 plus alpha times delta T in third power. So now we have this equation, and we need to recall from algebra that a plus b in the third power, that will be equal to a in the third power plus 3 times a in the second power times b plus 3 times a times b squared and plus b in the third power. So keeping this in mind, now we can write in a different form our expression. So that will be, by the way, this stands for V initial. So we can write here V initial times unity plus 3 alpha delta T plus 3 times alpha delta T in second power and plus alpha delta T in the third power. So now we need to recall, we mentioned this at the beginning, that thermal expansion is quite small, and that's why it's difficult to measure this thermal expansion with high accuracy. So means that in the small temperature range, when delta T is not very large, the product of alpha times delta T should be smaller than unity, because alpha is a very small coefficient. So if it's smaller than unity, then alpha times delta T in second power and in third power will be much smaller than alpha times delta T. And we can just neglect with these components, because the major contribution will be originated from these first two, 1 plus 3 times alpha delta T. So we can simplify this equation with some approximation, and that will be equal to, so let's write it from the beginning. We have V initial plus delta V should be equal to V initial times unity plus 3 alpha times delta T. So now we can divide left and right side by initial volume, V initial, and we will get the following. So will be unity plus delta V divided by V initial equal to unity plus 3 times alpha times delta T. So with this we cancel, and from here we can write that delta V is equal to 3 times alpha times V initial times delta T. Initially, like when we started to consider this case, we wrote that change in volume is expressed as beta times V initial times delta T. Looking at these two equations, we see that beta, which is volumetric thermal expansion coefficient, is equal to 3 alpha, which is 3 times linear thermal expansion coefficient. So this relationship can be useful in certain problems when one parameter is used, but you need to operate with another one. So just keep in mind this relationship. So with this, I think we can finish our today's discussion. We will proceed further with some unique properties of water expansion shortly next lecture. And our focus will be already on microscopic description of an ideal gas. So during this lecture, we introduced main concepts of thermodynamics and such important microscopic parameter as temperature, discussed in details how temperature can be measured, what are features of the liquid thermometers, which we should keep in mind when we design some liquid thermometer. Also considered constant volume gas thermometer, which provides us ideal linearity of pressure versus temperature dependence within very wide temperature range. So that helps us to define by interception with the temperature axis this linear dependence, the position of absolute 0 Kelvin temperature. And also we found the relationship, quantitative relationship between the thermal, volumetric thermal expansion coefficient and linear thermal expansion coefficient. Okay, thank you very much for attention. If you have questions, you're welcome. If not, then we will meet next time on Wednesday. So until then, take care. Have a good day and see you next time. Bye-bye, guys.
Thank you. Goodbye.
Thank you. Goodbye.
Bye.